Welcome to the fourth UAM Feasibility Study webinar. Today, we dive into the airspace architecture. Over the past 4 months, we have collected valuable data through our questionnaire, and we're nearing the finish line of this journey. A heartfelt thank you to all who participated in this survey. Your responses have provided us with exceptional insights into the communities and stakeholders' preferences and opinions regarding various aspects of urban air mobility. With just one more phase remaining, we are thrilled to announce that a comprehensive report will soon be released, showcasing Vertiports' industry-leading standards, and our approach is consistent across all projects, building from the ground up to enable urban air mobility integrations within cities and facilitating the seamless flight of eVTOLs and drones through our cutting-edge Vertiports UAM airspace structures. In this fourth phase, we will present the proposed airspace architecture for the selected vertiport location. As in our previous webinars, we will begin by sharing the survey results. And without further ado, let's kick off the fourth UAM feasibility study webinar, the airspace architecture phase. I'm Sandra Formenton, CEO at Vertiports, and I'm thrilled to be joined by Stephen Philpott, our CTO. Next, please. So here, in terms of terminal building, stakeholders have emphasized the importance of a comprehensive signage in the vertiport design, ensuring a balance between quick visual understanding and detailed textual information. And it is also recommended that this design team incorporates a mix of pictograms and text-based signs throughout the terminal building and vertiports to facilitate clear navigation. Efficiency and security are also equally valued considerations. We have efficiency that encompasses minimizing wait time, ensuring a smooth passenger flow, utilizing technology effectively, and providing quick service. And in terms of security, of course, security includes data protection, physical security, and passenger safety. Striking a balance between efficiency and security is crucial for the safe and smooth operation of the vertiport. Again, we also have the user navigation. The user navigation within the vertiport system should be efficient while adhering to best practices for security. To meet stakeholders' expectations, the design team should create a visually appealing and functional vertiport design that combines elements of both art decoration and modern architectural styles, and also comfort. Comfort in the waiting area should be prioritized, and a combination of lounge chairs and benches may be considered as well. Next, please. In terms of transit, so the feedback from stakeholders indicates a strong appreciation for the importance of incorporating various transit options in the vertiport surroundings, such as like bus stops, bike racks, pedestrian walkways, and designated areas for taxi or rideshare services. And this reflects that stakeholders desire to create a well-connected and accessible transportation network. Additionally, inclusive design considerations were highlighted by 50% of respondents who expressed a preference for the installation of elevators and wheelchairs ramps in the terminal building. And this emphasizes the importance and the significance of creating an inclusive environment that accommodates individuals who need it. So again, furthermore, stakeholders demonstrates a preference for self-parking with guidance system and also an automated payment system, aiming for an efficient and, of course, user-friendly parking experience. In terms of terminal organization, 50% of respondents favored an approach based on flight destinations, and this signifies stakeholders' inclination towards a straightforward and intuitive layout that aids passengers in locating their boarding areas with ease. Next, please. In terms of materials and design, the preference expressed by stakeholders indicates a strong emphasis on energy efficiency, electric transport, balanced construction materials, and comfortable environments. And stakeholders show a preference for LED lighting, support for electrical charging station, equal preference for glass and concrete in construction materials, and a preference for centralized HVAC systems for heating and cooling. And these preferences provide valuable insights for the design team for the designing the terminal building and vertiports to meet the needs and expectations of users while aligning with sustainability goals. Next, please. There was also an anonymous agreement on the importance of rainwater capture and reuse system, emphasizing the commitment to resource conservation and sustainable water management. And regarding the exterior cladding material, 50% of respondents favored brick, known probably for its durability and aesthetic appeal. And when it comes to amenities, there was an equal preference of 21% for charging station, restrooms, cafes, or even information kiosk, indicating a balanced demand for these facilities. And lastly, we have retail shops. The retail shops received a slightly lower preference at 14%, but still represent an interest in offering a diverse range of amenities to enhance the passenger experience. Next, please. Additional key design considerations for the terminal building and vertiports. We have equal preferences for blue, gray, and black and white color schemes, and this suggests incorporating elements of both for a visually appealing environment. And 75% of respondents emphasize the need for scalable design to accommodate future growth of the vertiport. Stakeholders value the inclusion of green spaces for an enhanced and aesthetic and a refreshing ambience as well. And again, these insights inform, again, the design team. It's really important to keep that in mind. The design team decisions, ensuring a functional and visually appealing and sustainable environment. In terms of vertiport surrounding, stakeholders emphasize the importance of landscape elements, safety measures in parking areas, and charging infrastructure for electric vehicles in the design of the terminal building and vertiports, and achieving a balance between integrating with the urban environment and ensuring a clear boundaries is recommended. And these insights guide the creation of an inviting and secure environment within the vertiport. Next, please. In terms of security, stakeholders emphasize the importance of comprehensive security measures and specialized infrastructure protections for critical assets within the UAM architecture. And it is recommended to combine security personnel, surveillance cameras, and access control system to ensure an optimal security. And the design consideration should include tailored protective measures for critical infrastructure, sensitive data, and advanced technology systems to ensure their robust security and safeguarding is in place. And lastly, we have the operators. So stakeholders highlight the importance of providing dedicated space for eVTOLs operators to conduct flight simulation and training at the vertiport. And this demonstrates their recognition of the significance of safety and competence in eVTOL operations. The design should include both indoor and outdoor training spaces to accommodate theoretical training, virtual simulation, and practical exercises, ensuring a comprehensive training for eVTOL operators and enhancing their capabilities. We are done with the survey. So I know you all have been waiting for the airspace structure phase. It's complex, but not complicated. So here we go. Today's points are going to give you a complete picture of what a UAM corridor might look like in the selected location. So our webinar today centers on the current and future landscape of urban air mobility airspace. We initiate with a comprehension of the various UAM airspace factors, which include aircraft specifications, logistical consideration, and the existing infrastructure's capability with both airspace and ground space integration. Next, we will focus on the prospect of UAM-dedicated airspace. Here, we will touch upon innovative concepts such as vertiports, sectorization, and cutting-edge technologies such as four-dimensional trajectory-based operation and ground-based public sensing node system. And moving forward, we will spotlight the software-defined airspace platform. This is specially designed solution that efficiently manages UAM traffic. And following this, we will converse on transitioning towards hyperlocal functional airspace blocks to integrate UAM operations seamlessly. Next, please. So let's get started with the current airspace surveillance gaps. So while high altitude airspace augmentation system and the ground-based airspace augmentation system play significant roles in our current air navigation infrastructure, they present certain challenges when applied to the new dynamic of UAM environments, particularly in managing commercial low-altitude traffic. And existing radar and satellite systems are not optimally designed for UAM ecosystem, as they present limitation in aircraft surveillance. So here is a view on an app. Commercial drone operators, like in our MyScout ConOp, utilize a low-altitude authorization and notification-enabled apps to display airborne vehicles, no-fly zones, and relevant airspace classifications such as Midway Airport Class B airspace. And this app does not allow our drone pilots to accurately determine the position and speed of other aircraft. And it's important to note that a significant portion of UAM flyable sectors are outside the jurisdiction of Class B air traffic control. So this is a snapshot of the Chicago airspace of our mock project. And this shows you that the drone no-fly zone, which is within the Class B airspace for Midway Airport, but on the edge of the control zone. So if you are flying 400 feet to the ground, there is a significant airspace surveillance gap that exists. So our one current consideration is the use of ground-based airspace augmentation system. So while the ground-based airspace augmentation system is suitable for the diverse flight paths and low altitudes associated with helicopters, it may not fully meet the requirements of UAM traffic surveillance. And here is why. So in the current commercial aviation framework, flights to and from airports are managed using a combination of air traffic control services and airspace management procedures and technology. While the specific techniques may vary, here's a general overview of the process. So when an aircraft is ready to depart, it obtains clearance from the ATC tower and the departure airport. As the aircraft ascends, control is transferred from the tower to the appropriate en route ATC facility. And as the aircraft nears its destination airport, it enters the terminal area. And arrival procedures involve coordination between the en route ATC and the ATC tower at the destination point. Radar system at the destination airports and ATC facility track the aircraft position and provide continuous surveillance during the approach. And those systems can see an aircraft from 30 to 50 miles away, and that's because of the altitude of the aircraft. Next, please. Thank you. So in traditional airspace, I can see an aircraft either with my ground-based satellite or my airspace satellite, 30, 50 miles away, depending on the placement of that radar. With the UAM ecosystem, it's common for UAS to be prohibited from flying from about 5 miles of the airport. Now, the reason why those airplanes are seen by those traditional tools has to do with the proximity of those tools and altitude. So if I can remain in an altitude where is the zone of sight of those tools, I can be seen. With a UAM aircraft, the closer I get to the airport, the lower I'm going to fly, and that's not the same as flying into an airport. But if there is a delivery to be made, or a passenger or a cargo transit within the control airport, the UAM aircraft will be beneath that airspace. And let me show you what I mean. So you have the facility map, which shows no flight zones for urban air mobility. Let's call it drones vehicles at this point. It's 500. And as you get closer to the airport, the drone altitude has to decrease. So the FAA recommended a hockey puck type structure around the drone, roughly 250 feet above vertical airspace between manned vehicles. And depending on the UAM aircraft altitude, this will create 500 feet tall hockey puck. And also 2,000 feet between the aircraft, so tip to tail. So through that zone, you have that much of a buffer. And when we talk about traditional airspace, remember, as those traditional aircraft are higher up in the air, it's easier for radar and satellite to capture them. In the case of these drones, either departing or arriving into this airspace, they are going to be lost because of the ground-based radar, because of its low altitude and proximity to the radar and satellite, and because of its granular, smaller footprint in that radar signature. So there is a real issue with regards to the current system ability to see, surveil aircraft, and that's the real component of safety that we depend upon in traditional aviation and airspace. So let's talk about these issues. We looked at them for years, and the NASA Dallas-Fort Worth use case with Joby really fleshed out a number of different points. We rooted them in these 6 points here, and they're all based on radar and satellite concerns. These concerns form a set of fundamental shortcomings that are primarily linked to the low altitude and shorter flight routes characteristic of urban air mobility. The root problem emanates from the inability to establish or maintain initial radar identification within the ATC system, leading to a loss of sight of UAM vehicles. So in essence, UAM exposes substantial operational safety gaps in airspace over cities. And as we envision denser flights and increased aircraft volume in the future, these challenges are expected to become more pronounced. So firstly, we address the issue of radar shadow, and this pertains to regions of airspace that radar cannot detect, creating a blind zone that aircraft could potentially exploit. And maintaining visibility and control over UAM vehicles becomes a challenge due to these radar shadow zones, intensifying the complexity of UAM traffic management. And secondly, we face the impracticality of the traditional radar separation requirements in the UAM context. The conventional standard of 1.5 miles lateral or 500 feet vertical separation for departing or arriving flows doesn't accommodate the unique low altitude and granular nature of UAM flights. And this makes the current separation protocol less suitable for UAM operation. And moreover, UAM flights often enter the shadow zone or radar blind spot almost instantaneously after leaving the facility map zone of Class B airspace. This radar blindness escalates as the UAM vehicle distance themselves from the vertiport, adding yet another layer of complexity to ensure safe and efficient operations. The issue of radar screen clutter is a substantial hurdle in managing low-altitude UAM traffic. And this visual noise on radar screen arises from a myriad of sources, including ground weather conditions such as rain, atmospheric turbulence, animals, and even insect activity, and most critically, the small profiles and flights envelopes of eVTOLs and drones. And even a seemingly minor 5% increase in airspace volume can lead to occluded radar returns, increasing the difficulty in air traffic control oversight. And this clutter can obscure or mask UAM aircraft creating significant challenges in maintaining an accurate picture of the airspace environment. Aircraft masking is another considerable challenge in the UAM environment, and this arises when radar resolution, which captures a larger volume of airspace, the further the aircraft is from the radar, leads to potential masking of UAM aircraft flying beneath traditional aviation within the radar's reception cone. And in such cases, multiple aircraft may appear as a single contact on the radar display. So this amalgamation of signals, referred to as masking, can occur when multiple UAM vehicles fly in close proximity to each other or near each other or other obstacles such as buildings. And this masking effect can cause visual noise and confusion due to the overlapping display of multiple aircraft IDs, creating difficulties in accurately tracking and monitoring UAM vehicles. And this in turn escalates safety risks and increases the potential for collision. In terms of aircraft sequencing involves giving precise flight instructions to maintain appropriate spacing between aircraft, primarily in arrival and departure scenarios. As highlighted in the NASA use case, the FAA ConOps suggests that ATC will not provide tactical separation services to UAM flights within corridors. And this means that traditional ATC separation management in UAM environments could lead to a significant increase in workload, volume, and complexity. And moreover, traditional airspace surveillance tools are not adequately equipped to handle this task. So unlike traditional airspace, which is divided into several sizable regional zones, UAM requires zones that are smaller but significantly more numerous. And current system and standards used for identifying waypoints, flight lanes, and landing zones, which work effectively for conventional air traffic, fall short in addressing UAM's requirement. And this necessitates the development of new technologies, methodologies specifically tailored to UAM airspace management. When it comes to remote ID, this is an issue as well. So the remote ID is a concept that involves each UAM vehicle broadcasting its position, identification information such as serial number or session ID, as well as geographical location and velocity. However, realizing this concept presents a set of challenges. For instance, the system requires the broadcasting UAM aircraft to fly within a maximum of 150 feet of the remote ID receiver for effective capture and reporting of UAM position, navigation, and time, so the PNT. Moreover, the current state of the infrastructure might not support the necessary range for remote ID, posing difficulties for UAM operators and air traffic controllers. So thank you. Steve, this is yours right now.
Thank you very much, Sandra, and thanks for providing the overview of where we are at this point. I want to thank everyone for continuing to join us as well as providing input into our surveys. We're going to talk about our actual approach to airspace structure design relative to UAM. Our approach was developed initially in 2015 as a concept, and then in actual design and test development of a scaled down prototype in 2017. The approach considers standard recommendations by the FAA Vertiport Engineering Brief 105, our ongoing participation in the EuroK working group 105 and additional downline discussion groups, as well as the FAA NASA UAM blueprint and other publications from the ASTM. The basis for the design is rooted in the current TCAS system, or the traffic alert and collision avoidance system, which is used by traditional aviation. It's an airborne system that operates independently from the ground-based air traffic control system. But what it does at the end of the day is detect the presence of aircraft, transmit at a very steady rate the information, PNT, for example, very frequently, and then employs a receiver, typically on the aircraft itself, to receive these and reply to these interrogations in a standard manner. So this is our approach. So what we wanted to do was be able to capture these types of data points in our design and then digitize them for a new approach. So in doing that, we decided to develop the nomenclature, which is essentially the definitions for all of the places and things and activities that will occur within a UAM airspace structure. In the context of software-defined airspace, which is our own approach, we're looking to use the nomenclature as a system of naming and technology to standardize the various components of a software-defined airspace unit and those entities and concepts within the framework. So if you look at what we have is essentially vertiport airspace structure definitions, the actual airspace structure sector, the broader sector in which it sits, the corridor structure, so that's basically how to get in and out of those software-defined airspace structures, and the route types. What are those route types going to be? And the zone types, along with what are we looking for to encourage deconfliction and traffic management. And then we look at the broader area in which those aircraft are going to be traversing. We also look at developing a lexicon. And so let's call the lexicon the base of knowledge of relevant objects that refer to the object's characteristics. It is essentially each one of these are placeholders for the identifiers and characteristics of those objects. And the goal is to provide a standard lexicon to grow with the robustness of the UAM industry and provide a reference for that growth over time. And within our approach, we define the lexicon to capture information like the sector layers themselves, the digital twin of that sector in which we fly, the digital rules of flight within that sector, and publishing of that information to the relevant tenants of that UAM ecosystem. So let's talk a little bit more about the actual urban airspace. And so when just to take a step back, everything that Sandra said kind of mentions that the existing traditional airspace system is going to have a hard time being retrofitted to accommodate the new type of vehicle. So when we're talking about vertiport airspace, we're talking about urban air mobility airspace designated specifically for UAM aerial vehicle operation within that defined airspace, as well as the integration between the other low altitude airspace vehicles, unmanned, manned, drones, air taxis, and otherwise, and other aircraft, manned and otherwise, that are traversing in and out of that airspace. Computers moving a little slow here. So let's talk about our proposed location. We're at 6200 South State in Chicago. We captured a bunch of information to determine where that location is and what our route capabilities were, as well as the actual sizing of the vertiport. That vertiport size, we took into account the dimensions of the vertiport itself, but we want to establish what we call the D value. And that's essentially that airspace that is significant to the operations around the airport, the boundaries and dimensionality of that vertiport revenue. And so we have taken the same approach of using a facility map, a UAS facility map, to bridge out or step out the altitudes, the maximum altitudes of aircraft entering those zones to provide that basic standard of protection. And then we kind of drew a circle around the vertiport to define that maximum area. And we're going to call that the critical flight zone, or the aerodrome control zone. It's our vertiport's sensitive flight zone. We're going to say, for example, that is 1,200 feet. There are no obstacles. There is clearance from the vertiport out to 1,200 feet. And then we look at that sensitive zone around that. That is the exiting of the critical flight zone of that vertiport into the Class B airspace. It may be beneath it. It may be entering into that airspace. But we want to define that area as the D value of that sensitive space to get the vertiport's true D value of about 1 mile, about 1 mile. We also want to look at various angles of approach to get in and out of that critical airspace and the sensitive airspace. It's a little wider on airports because of the vertical flight characteristics of the manned aircraft. We looked at, since all of our aircraft will be vertical takeoff, we looked at the best possible and most efficient way to enter and exit those zones. In traditional airspace, there are fixed points. An approach fixed point is a designated location on the ground, if you will, used by the pilots to initiate a final approach. So you've got approach fixed points that are typically a few miles from an airport and designated on your aeronautical chart by a symbol. And then of those type of points, obviously you've got initial approach fixed point, then you got a final approach fixed point. Let's say that initial approach fixed point is outside, just entering the sensitive zone, where that final approach fixed point is that area where you're actually coming into the critical flight zone. And this would be the point in which a pilot or the operator would encounter communication with the traffic management system to acknowledge their position and indicate their final approach and descent into that landing area. So by capturing all of these data, we're able to create a clear snapshot of the footprint that has the activity directly related to the vertiport itself, right? So just like the aeronautical chart, we will need to present these types of areas with these types of data in an analog fashion. Our approach is to bring that approach into a digital communication structure. Now, the second thing we do is look at the sector airspace, right? So in our area in Chicago, we are looking at the broader mileage around or from the vertiport's airspace. In our standard, we consider our minimum sector size to be roughly a 3 square mile area. Some of these indications on here may not depict 3 square miles because one of the projects or one of the tenets of the project that we're looking at actually extends that sector a little bit further. But for the sake of our basic design, we're looking at a 3 square mile area around the airport. And our true goals are really 3 things. And they are to look at the accepting airspace coming into the area, look at the no transgression zones that are all around, within, and external to the area, and then identify those path segments to get you in and out of those areas efficiently. So taking the same approach where we're looking at the vertiport airspace and the sensitive area of the airspace, we're going to first build the walls of our software-defined airspace platform for this particular sector. We're going to take that information from the vertiport's D value, and we're going to create a square mileage and then label the vertex or vertices, the 4 corners of the sector with the longitude and latitude. This gives us the characteristics by which we can identify the area. The process for building the walls is really the two components: define the geographical boundaries and establish the altitudinal limits. So the sector index, that is the main corner of our sector, is going to be that vertiport. So you see this here, that is essentially, this is the main corner. That's our primary vertex, right? And that's going to be used to give us reference points and waypoints for the entire sector. We also create secondary vertices to identify other waypoints, midway points, and distances across the XY axis of the software-defined sector, or as it's often referred to across the pond, a functional airspace block. In doing so, determining these primary and secondary vectors or vertices within our airspace block, we can now start to think about those accepting areas. So in traditional airspace, we know where a aircraft will report that they are a type of aircraft and that they're on approach. Well, we want to standardize those positions for each vertiport, primarily for safety and predictability. So at the end of the day, it gets pretty simple. You're either coming into the airport or you're exiting the airport, and we want to designate specifically where there is going to be. In the European construct, these functional airbase structures or blocks are vital for reducing the airspace fragmentation. They're necessary to accommodate steady growth in traditional aviation traffic and to minimize delays more dynamically. So we mirrored that key element, the accepting unit, in our design for software-defined airspace. Then we define the no transgression zone. So in traditional aviation, the NTZs are identified for obvious reasons, right? In our feasibility study, we still need to determine what specifically those areas are. They're comprised of really the airport control zone. These are all standard nomenclature items. Airport control zones, prohibited areas, restricted areas, temporary areas, airway corridor restrictions. But overall, the ACZ is kind of our essential primary NTZ that we're looking at. It's the airport controlled zone of Midway. It has primary rights over our integration into that airspace. So you look at the types of NTZs that are typical. We know that they're probably going to be our first responders, our good guys out there doing the hard work, as well as that airport. So we want to consider those zones primary NTZs and place them on our maps. Secondly, we want to put in those airway corridors so that we can identify where activity will occur and where those inflection points might happen for deconfliction. And those corridors are the airport's lanes of travel. When we originally designed the vertiport, at least looked at the boundaries, we looked at the alignment with the primary airport in the area, which in this case is Midway. So what you'll see are flights that occur almost directly over our vertiport. However, we want to make digital consideration for our flight and the integration of those flights. And so to define the lanes of entry into the UAM zone, we are basically going to look at the pathways, if you will. And the pathways consist of corridors that should be designed to maintain separation between the aircraft, manned and unmanned, and specifically looking at the mobility that would occur within the UAM sectors corridors and the air taxis, for example, that will be traveling to and fro and entering and exiting from the Class B airspace. So there are a number of factors, basic factors that we had to consider in design. The first, obviously, is safety. The second is the integration points and the right of way to get in and out of the Class B airspace, or at least the civil aviation airspace. That includes the vertical integration, the reporting points, and the clarity of the zones, the flight zones, what type of activity can occur. We want to also look at the airspace capacity and the potential traffic volume of that sector. What is the planned capacity? What is the current capacity? What do we need to plan for? Is there an event nearby where the airspace traffic will increase and we need to augment our various deconfliction zones with additional algorithms at that point in time? We also want to look at the objects of the ground space. So where we say tall buildings here, we really want to look at any obstacle or structure that could pose a unique challenge, including tall buildings, of course, but any type of infrastructure that could be considered an obstacle. And we want to chart these within our system to minimize the potential conflicts or hazards when having to interact in those areas. And then lastly, we want to look at the addressable policies and preferences of local UAM operations as considered by the public. Public acceptance is the #1 factor when being kind of certified or allowed to activate these UAM sectors. So engaging with the public and local communities in the design process is what we've shown in our survey approach. But in an actual feasibility study, we go further to help address concerns, provide information about the process and opportunities, as well as ensure acceptance of these pathways. And this might be everything from looking at our engagement for public consultation to talking about aircraft noise concerns or pollution concerns, or even the visual impact of flights over these pathways. When we designed our pathways, we looked at the ground space. In one of the first webinars we talked about, we align our designs with the existing ground space, ground traffic routes. And so our coordination with air traffic control of these routes has to do with ensuring, again, that separation between aircraft, both manned and unmanned, and their compliance beneath and into the Class B airspace. And we wanted to make that as simple as possible, because in most cases, the air traffic controller themselves will not be interacting. It will be a system of reporting. And we think those reporting points will have to do with the pathway corridors, routes, and sprites. In designing the pathways themselves, we just look at those routes, those lanes, those approach areas that are going to consume primarily the airspace of our vertiport. We employed a meticulous approach to designing the corridors, the paths, and the pipes, and we'll talk more specifically about pipes a little later. But the most important piece was the consideration of the establishment of dynamic entry and exit points for the zones based on the altitude. So when you see these green lines here, there are altitudinal differences in various paths. That is, there may be a set of pathways at 50 feet, a set of pathways at 150 feet, on and on and on to the maximum altitude of 400 feet that exists today. In developing the pathways, we have all of those elements of the descriptive points considered. So the 40 TRV, which we're going to talk about a little bit more, which is the brain box of the system, and the accepting unit itself. How do we get in and out of there? And then what are the rules of that? And where do those rules come from? And so developing all of these data points is integral to basically building out that data set that will report the information that will provide the ability for traffic management as well as dynamic deconfliction. Excuse me. The digital flight rules approach in urban air mobility is supported specifically by our approach to software-defined airspace and its related technologies. The aim is to establish a robust regulatory framework that enables the safe and efficient coordinated operation of the system. But the rules need to have a layered approach, whereas the digital systems and the data exchange provide enhanced situational awareness. They manage the traffic in a dynamic way, and they ensure it's compliant with airspace restrictions, local concerns, and definitely the concerns of the folks whose heads over which they fly. This will ultimately foster true and effective integration of the UAM into the existing avionics areas, the existing aviation ecosystems, as well as into a city's transportation operation. The digital flight rules, our approach, we've developed the digital flight rules to take into consideration the inbound and outbound integration points from the UAM vertiport. The digital flight rules may identify the sector types to categorize and define the specified areas where the specific type of UAM operations can take place. And the reason we went a little bit further to provide a systematic approach to capturing and publishing the digital flight rules is because they will vary most likely according to the altitudes. So in one level of altitude, you may have one type of activity, and another altitude, you'll have another type of activity. But at the end of the day, a special consideration is given to the areas with the highest traffic volume and the most potential incident points. So these are the areas where UAM operations are going to be most concentrated, and in densely populated areas or in transportation hubs or specific regions, these things are critical. So for example, we said that overflight areas will probably account for 25% of the activity that occurs in a sector. And then a full 50% might be transversing in and out of the vertiport, a full 50%, right? So that's a real point of activity to be concerned with. And then of course you've got those aircraft that are going to be entering the sector airspace from the ground, and those aircraft that are going to be sitting on the ground. So in this example, we said our vertiport is going to have about 25% of the aircraft that are initiating from the vertiport into the airspace, and then 10% of those aircraft are sitting on the ground, charging, being loaded, or what have you. The implementation of a route, of a system of routes, is based on capturing the characteristics of the walls, right? We talked about those walls, or in, I guess, technical speak, we're talking about the edges, those points between the vertices that extend up to a specific altitude, right? So in those walls, we have created those rules, and those rules will also vary on an X and Y axis. Our ultimate goal is to capture all of the activity, movement, data that occurs within the UAM airspace block, or the vertiport operational block, for the basic reason of transportation management, but also to capture those touch points so that we can ensure the billing and revenue potential for the vertiport operator and the downline city that collects the taxes on this. Everything that occurs within the airport sensitive airspace will be seen, but the 4D TRB, which is the brain of the system, truly is able to interact with 75%. And again, we said 75% is going to be that grouping of aircraft, manned or otherwise that enter likely into that 500-foot layer, that 100-foot buffer over our sector. So we'll also be capturing information about them and essentially speaking at a certain point in the process of development, but speaking to those aircraft to encourage the correct communication for safe flight. So here's a depiction of what a notional functional airspace block or sector would look like with route labeling lexicons. So you essentially have that top layer, which is the Class B airspace, where a WAAS type system is going to be providing the surveillance of those aircraft in that space. And then you've got that buffer zone. After that buffer zone, you have our actual sector walls with their characteristics and their lexicon, which can hold information. So Vertisky employs the zone and route labeling approach within the 4D TRB, which is the 4-dimensional trajectory based operational block. 4-dimensional trajectory operations box or block. Anyway, within the sector, and enables that sector to kind of see those objects both on the ground and in the air, their structure, their characteristics, and this understanding that entire playing field actually helps prevent collisions because it provides more predictability and ensures the efficient movement also of the UAM vehicles. It normalizes the flight standards to help identify the odd man out or bad actors. If we can make the aircraft routes, their activity within their routes standard, we can understand when things are not going well, and we can respond to that instead of having to identify that later. Excuse me. So the use of the zone and route labeling enables us to enforce the compliance of not just the regulatory requirements and operational guidelines, but those rules of airspace is put forth locally. And at the end of the day, different sectors, different cities, different vertiport airspace managers may have different requirements. So the digital flight rules stack within our 4-dimensional trajectory reference box within the software-defined platform can be appended to include various additional parameters or other considerations like altitude restrictions, speed limits, noise restrictions at a given point, routing and waypoint guidelines to understand. You would be able to insert weather and microclimate data, such as urban canyons, so the gusts that occur between buildings, and environmental considerations. And also special use airspace. There'll be times where there's an event or there is a first responder situation in which that layer will dictate or identify, dictate, and publish what needs to occur. So you're able to add those layers in our software-defined airspace platform. As I mentioned, we're developing the software-defined airspace platforming using Chicago as a use case to provide this visually, digitally scaled down, demonstrable version of a UAM active ecosystem. And we've done this by implementing the functionality of this SDA kernel, the 4D TRB. And to visually represent the SDA-enabled sector and its geo-referenced points, we use ground-based sensing arrays to capture the airspace movement, as well as a secondary approach to capturing the ground space movement too. So right now, let's talk about the ground-based public sensing network. The project that we employ, or our approach to the project, aims to extend and reactivate an existing unused node array and use it in the urban air mobility sector. So this is an application of an existing set of technologies in a different industry application. So this innovative use of the ground-based public sensing node model builds upon the technical advancements already proven out by the Argonne National Labs Array of Things team, the SAGE Continuum Project, and this has given us a lever for partnerships, this information, this background, this experience to use in our approach with the NASA UAM DIP and the UTM project. So by repurposing the unused node array and using it with UAM, we introduce a novel solution that addresses the challenges of airspace deconfliction and aircraft detection. So when we talk about building that box a while ago, and this is not oriented the very same way as our other, where our vertiport index was. In this case, our prime index is V1, and our vertiport would be somewhere in here. But we're going to place those nodes along those defined primaries, those primary vertex or vertices, and then those secondary vertices. And so each vertex will have its own node with its own characteristics, its own geolocated description. And what we want to do is create a base of node density that will give us the data we need across the edges and throughout the altitudinal layers to achieve what we call sensor fusion. And ultimately, that is a correlated data set that gives us a snapshot of the integrated activities of the sensitive airspace, as well as all of the airspace that occurs within that vertiport's control zone. Now, taking this approach, again, we use those boxes and we label those boxes and we create those rules and we do all that good stuff to simulate the movement of the drones, or at least capture the movements of the drones within the SDA sector, okay? So capturing all this information is in addition to those definitions that we put into play to capture the air traffic, the flight paths, the altitudes, the digital flight rules, compliance measures. At the end of the day, we also want our users to be able to understand how to use this sensor fusion capability to incorporate additional relevant layers in and get reporting that will basically allow them to apply premium features, such as being able to geofence or provide a geofence alert to aircraft in the sector, or just zoom in and out on different activities within that sector to see more data about the aircraft or the operator, things of that nature. So in capturing all this data, both the active data and the defined data of the sector, we want to cull it into a UAM data set. And we want to communicate that open UAM data set to the national airspace. So we'll publish our data set from each sector from a UAM sector cloud. So Vertiport Chicago, I'm sorry, the mock feasibility study of Chicago, that location sector would have its own cloud, which would cull that sector data. And as it's processed on the edge by the nodes in close proximity to the UAM aircraft, and then using our core member API with the NASA UAM or UTM, these data sets will be published into the NASA DIP for role-based authentication of us, and then exposed to the National Airspace System through the FAA. So at the end of the day, we want to offer this UAM, this open UAM data set as a free data set that cities can use to provide this basic level of traffic management. Now, Vertisky Group, ultimately, we're a for-profit company, and our approach is to use that open UAM data set and correlate additional data into more complex command data sets or navigation data that will take more robust machine learning and computer vision data and reasoning blocks, building blocks, to accelerate the refinement of operator service data within a UAM sector's ecosystem. So let's talk about that just a little bit more. The function of our software-defined airspace platform at the end of the day is just to give cities kind of a fingertip access to a switch where they can turn on their various sectors and have this safe harmonization of urban air mobility and the traditional manned airspace operation. To accomplish this, Vertisky integrates with the NASA DIP, Digital Information Platform, via that API interface I talked about. And this is where the flight data is fused and mediated, typically from multiple sources, such as the FAA's system-wide information system, or from airlines, their specific data and other sources themselves. So in our way, the use of this NASA resource, the DIP, as well as their UTM resources, will assist Vertisky in development of low latency environments, the sectors themselves, and for enhancing the UAM data services, as well as shrink the capabilities gaps for cities to manage their own airspace, provide the benefits of UAM, and also generate revenues. Start. Okay. Where the UAM industry is somewhere around, and to be optimistic, we are somewhere around UML2 in terms of maturity level, where we want to be and what we want to provide. The software-defined airspace approach will provide the level of complexity to scale from UML2 all the way through very seamlessly to the full extensibility required from UML6, let's say. We'll evolve our API towards the use of these NASA FAA machine learning ecosystem blocks, the catalog of their existing tools as a resource to introduce efficiencies, reduce the technical barriers that may be in place and NASA's already solved. And some of those resources that we've identified for use are their data storage system, where their fuser data is stored in relatively a fundamental RDS type of database. Their machine learning ecosystem, NASA's developed a machine learning ecosystem in their cloud services, where we can access things like KPI reporting services, health monitoring of a sector itself or the aircraft in that sector, reusable prediction microservices to reduce the need for standard adaptations, as well as other services that may be available and provide the system a much more robust capability. So our traffic management approach is really based on that brain box, that kernel, the four-dimensional trajectory reference box or block, to provide this hybrid conflict data management system, capturing all of the data within that sector, assigning characteristics, and then publishing that information back out using all of its system capabilities. Folks have asked, well, how do you, if you're going to build a 3 square mile minimum sector, how do you connect these things? Well, we do this through a data mesh strategy, and that strategy supports the seamless exchange of data between those sectors to coordinate safe operations. But we want to be able to show the contiguous UAM sectors, whether they're together or just the next sector. We want to be able to show those data points as defined by those geographies, right? So sector 1 equals a number of geographies and a number of activities and a number of obstacles and objects. Sector 2 may have additional information. We want our strategy to offer a number of technical advantages, such as the decentralization of the architecture, so that a city itself now has its own picture that it can present, control, and store. You have domain-oriented ownership of this data, where a city or a vertiport controls that data and the efficient data discovery within that data, and the interoperability with systems that are connected with the National Airspace System, NASA's DIP, other UTM strategies, and then provide the scalability that we need for collaborative innovation in the future with other airspace operators, partners, and so forth. So at our root, we are looking to focus on the basic use of kind of some simple algorithms and developing and implementing advanced algorithms for aircraft detection, threat assessment, resolution advisories within the context of UAM, and take that core data that's being processed on the edge by our ground-based public sensors network and use these data in a way that kind of take the burden off of manned interaction. So in this case, you see the example, we're using a best path algorithm, Dijkstra's best path algorithm to go in and out of the sector. And so again, in that four-dimensional trajectory reference block kernel, the kernel itself, we're gonna have all of these data points kind of crunched down so that we have PNT data. And the PNT data within the SDA provides the information about the location, velocity, and orientation of a UAM vehicle at different points in time. That's kind of it. At its core, that's the core data that is crucial for understanding the dynamics of a UAM operation. The open UAM data set provides a valuable resource also for researchers, developers, and other stakeholders in the UAM ecosystem to study and analyze the interactions between that PNT data, those objects that are moving, and provide more robust command instructions in the context of UAM operations, airspace mitigation, as well as just traffic support overall. So we take that PNT and then we look to build out additional data sets that are important to that ecosystem, right? So beyond where that aircraft is, we want to be able to do a number of additional complex things. At the end of the day, the true end of the day, publishing the information is where we excel. It's that integration between that city's 4D TRB, the regulatory environment, as well as the operating environment that allows the UAM ecosystem to flourish. So we look to a standard interface. We talked about the interface with the NASA UTM, the NASA DIP. We want to provide a standard generic interface which allows the SDA to share data to UAM operations. We want to share things like flight data, the routes that are planned, vehicle trajectories as planned and as they are, airspace constraints planned and as they are, all things that will occur within a city's 4D TRB or their contiguous 4D TRBs. This exchange of information enables the city to incorporate UAM operations right away into their overall traffic management strategies and help with the balancing of traffic in their urban planning strategies moving forward. With the constant data on each of those sectors, urban traffic just flowing all the time, including both airspace and ground space, we can capture a comprehensive picture that will, in no uncertain terms, lend to the overall safety that is required of UAM. In this case, you see on the left, our city cloud. So this is the origination point really of where that data occurs. And on the right, you see the NASA DIP. And this is where the information is kind of correlated, bunched, and then republished back out to the regulatory systems. In our case here in the States, the FAA. So we're taking that basic UAM data, putting it out and making it available in a number of different ways through these partners that will have API access, if you will, to the data that occurs in those sectors. So the SDA and the 40TRB operating system represent a comprehensive platform for managing UAM operations within a city. It's as simple as that. It leverages the concept, the proven concept of four-dimensional trajectories, which support dynamic route optimization, traffic conditions, airspace constraints, weather, operational requirements for the good of that particular sector of the industry. Let's talk a little bit about the 40TRB. By applying the SDA framework, the concept of avigation, which is really defining direction and rules, it's extended into the integration of the commercial low altitude activity by those aerial vehicles. So this framework will play that crucial role in analyzing the airspace, but it also promotes the use of that airspace in a standardized fashion. So what we're able to do in our airspace design is employ those regulations and policies, traffic management, integration with existing aviation system, infrastructure, and other safety considerations, and ultimately create what will be an analog version of a UAM aeronautics chart, which will basically give you all the information about the airspace over a sector. The complexity involved in culling and correlating all of those data points that we've talked about is ultimately an infrastructure investment by a city, to be honest with you. But it will facilitate a range of air taxi and drone operations. So where that infrastructure investment may seem to be outside of the scope of a city's transportation management strategy, enabling eVTOL cargo movement beyond the visual line of sight flight and operations, truthfully, in dense urban areas is a win, is a huge win. And what we wanted to do is give that ability to provide a visual representation. In our published study, we will identify and label the actual flight routes, the main flight routes in, and the transition points. In this case here, transition point we're calling a sprite, and it's the movement between altitudinal levels and into additional routes. And this is where those rules are applied. So if we took all of those data points and we took that sector information, those boundaries, and then took the activity that actually occurs and is active within a lexicon, ultimately a city would have that fingertip coordination. They would have predictability in terms of the operations that will be coming in and out of that sector, and be able to provide operators with real-time or near real-time information about airspace conditions and restraints. So that's our approach to airspace design in our mock study. Those are the tenets of it. We didn't go real deep into the actual development of it, which is something that we would do on a one-off basis with our clients. But we certainly appreciate the opportunity to show this approach, and that we have spent considerable time with our partners in what we think achieving an optimal platform for discovering the capabilities of UAM within a city, as well as activating UAM within a city. Our 40TRB, in our opinion, is the tip of the spear for cities to begin talking to operators about the footprint of their aircraft, the capacity of their aircraft, the environmental considerations, the precise trajectory preferences they may want to use, their noise profiles within different spaces, and they can talk about these things relative to specific ecosystems and not just in theory. So we are happy that these architectural components create a robust framework that supports the safe and efficient sustainable integration of UAM into a city's airspace. And we are thrilled to have the participation and support of our partners globally to affect the development, testing, implementation, simulation, and deployment in cities around the world. So I wanted to thank everybody for being here again. This is actually my last segment with my mug on the camera. Thank you so much for being here and your participation. Next month is our last segment in this webinar, and the end of the webinar is right around the corner, and we'll begin to compile the actual study. You have the benefit of meeting our world-renowned head of architecture and design, Mr. Giancarlo Zima, who will focus on the tenets of the actual vertiport architecture. And as Giancarlo is recognized around the world for many of his vertiport designs, he is also, I will call him, a scientist behind the crucial aspects of UAM implementation. So we hope you don't miss it. So thanks again to everyone for being here. Hope to see you on the 19th. This webinar will be earlier in the day as Giancarlo and our team are in Italy, different time zone. Thanks again to our CEO, Sandra Formanton.